So earlier today I was going through the uncertainty principle, and I've got some really interesting thing to share with you guys today. Here I'll be talking about how this Heisenberg uncertainty principle actually works. You probably know uh, the statement, so I don't want to go into that. But actually you need to know this one here. That is, the product of uncertainty in the position and the angular momentum of any microscopic particle will be either greater or equals to s by 4 pi, but we'll use this equal to sign here because we want to find the values, so we'll keep that equal to, but that's actually greater or equals to, and we actually get the minimum value here. Anyway, forget that. So what is the significance of this uncertainty principle? The significance is that in case of microscopic particles, the uncertainty principle is only applicable for microscopic particles. So in case of microscopic particles, uh, it's not possible to determine the position as well as the angular momentum simultaneously and accurately. So here you can see that's a nucleus and that's an orbit, and on that orbit there's this electron, so it's revolving around the nucleus, and I want to find the position of that electron. So what I will do is I'll use an electron microscope and shoot out photons from the microscope on that electron, and this is the photon. Okay, this is the light wave that will strike the electron and come back, and I can find out where actually that electron is. So I'm just trying to get an image of that electron by striking it with photon, that is light. So let me just say that I use a photon of wavelength lambda, and there will be an uncertainty of lambda, either plus or minus lambda, in the position of that electron. Okay, I strike that with a photon, I strike that electron with a photon of wavelength lambda, then there will be an uncertainty of either plus or minus lambda in determining the position. If I use a photon of high wavelength, very high wavelength, it will have low energy, so I'll get since it has high wavelength, there will be more uncertainty in position. But if I use a photon of low wavelength, it will have more energy, and when that photon strikes this electron with more energy, that's gonna just move away, and there will be a bit more uncertainty in the momentum because its velocity will increase. You probably know that the photon, this got more energy if it has low wavelength. So yeah, that's the uncertainty principle right there. And with uncertainty principle we can find out why electron cannot exist in the nucleus of an atom. So let us suppose that electron will actually exist in the nucleus. If that's the case, then the radius of nucleus is 10 raised to power minus 15 meters. You probably know that. And here I've got the uncertainty in the position of electron, and that's going to be minus 15 meters, 10 raised to power minus 15 meters, if the electron is inside the nucleus. I used the Heisenberg uncertainty principle with that equal to sign right there. I told you about that earlier. It's either greater or equals to, but we'll use equal to because we want to do some mathematics here. And yeah, what's the uncertainty in velocity? That's del p, guys, because mass into velocity is always momentum. So yeah, what's the uncertainty in velocity? That's gonna be 6 into 10 to the power 11 meter per second, and it's not possible because nothing can have more velocity than that of light. So that's Heisenberg uncertainty principle.